shaping this origami with curve folding by pulling strings. And
notice how the folding is not only guided by the thread, but also by the interaction of the crease pattern with itself until it locks into place. The Nautilus shape is based on a sphere crease pattern, that is, a pattern that folds to a spherical shape with parts bordered by curved folds, mapping to the cores. We computed a set of 325 candidate strings. The first solution yields impractically long string lengths, was scaled to the 2-meter long sheet. After pruning these very long edges, we obtained a second solution where we used 4 threads to synchronize the lengths of the contracting strings. Once again, the physical realization confirms the validity of our optimization of physically plausible actuations. We presented an algorithm to design computational mechanisms to facilitate folding of crease patterns, a process that has so far been largely restricted to manual folding. This opens up possibilities to realize movable, lightweight, large-scale freeform surfaces without requiring complex manual or robotic actuation. As key technical enabler, we introduced the notion of string actuation modes, and use them to select actuation points and decide how to string these points together. The crease patterns and stringing sequences are available on the project webpage for personal use. Thank you.
Actually, we can learn from their experiment and think of a way to fabricate curve folding shapes using this kind of string connection, and by changing the length of the string, so to control how this planar sheet of material can be bended. Okay. Victor, can you prepare, because I want you to share with everyone how you simulate the curve fold.
Okay, sure.
Hmm?
Okay.
Okay.
But it's very complicated.
Very complicated. Good, that's good. So we can learn something from you. Okay, so you prepare for that and then later, okay? So I think today what I prepare to discuss with you is about curve folding, because I think all of you, your project has something to do with curve folding. Okay, so this video I think it's very inspiring, and you should also try to read the paper they present. This paper was presented in SIGGRAPH. SIGGRAPH is the most important conference, international conference for computer graphics. But in fact, they do not limit their domain in computer graphics. They also do real things, such as this one. Okay, and it is very, very difficult to be able to publish your paper in this conference. So we can trust the quality and the contribution of this research group. Okay. What? Okay, and besides this video, okay, here I see here through this link, you can access their website. Okay, this is the website of the research group of this video, and there are 2 more videos. Let's take a look at this. Okay, this can be used in a fabrication process.
Curved folded surfaces hold a special place in computational origami. We introduce string-actuated curved folded surfaces that can be shaped by pulling a network of strings, vastly simplifying the process of creating such surfaces and making the folding motion an integral part of the design. We consider shapes defined by two-dimensional crease patterns that exhibit curved creases,
Okay,
and compute a sparse string graph on top of an input crease pattern, such that the physics
more or less the same as this one.
curved folded surfaces hold a special place in computational origami.
Okay, the same. And this is not a paper. Where's the paper? Okay, applications. Okay, and there's another paper. From origami to folded surfaces, representing moving forms. Very small regarding kinetic structure. Okay, so these are the aesthetic material, round rash pattern. Okay, sometimes people call it water bump, but I think more official or more formal way we should call it round rash, because round rash can be the first person who tried to use this pattern to make curved structures. This is also round rash. Yeah, this is round rash pattern. Group B, is this similar to what you want to do? Yeah? Yeah, I think it is similar. So the way to simulate the fold is you have a valley fold, okay? And then you have this kind of mountain fold. Ready, can you call this ready? Victor, how can I call this pattern? Radiosic or
Radio lines.
ready?
Radio.
I don't know. I mean, 辐射状。How do you call 辐射状 in English? Sorry. But you know what I mean, right? So maybe you can simulate this pattern. Don't look at this support. I mean, I think they try to do the structure analysis. And you have a valley fold, and then all the rest are mountain fold. And then you probably get something like this. Is this similar to what you think? No.
Kind of similar, but we have a.
But we only have this line is height, but they have 3 lines is height.
Yeah, that's right. But it really depending on where you define these two edge. You just move it closer to the folding line. Okay? When it is very close, then actually I don't think you feel the difference. Okay. I don't know. Maybe you have to test it. Okay. Yeah, this is the round rash pattern. And then this one we should discuss more in depth. You see, this is by Tomohiro Tachi. He's a professor of Tokyo University. He was graduated from architecture school. Okay, designing 1 degree of freedom, DOF means degree of freedom, which means you control the shape using 1 parameter. Okay, for example, like the curve folding by pulling strings, the video we have just seen. Okay, if there is only 1 string, or if all strings are controlled by 1 actuator, okay, then we can consider this shape also 1 degree of freedom. Okay. And Professor Tachi's argument is that if we have curve folding pattern and we define the rules of this curve folding, then this kind of origami become 1 degree of freedom structure. Okay, and because he's from architecture, so what he has been doing is more concerning architecture. Okay, by rationalizing curve folding. Okay, what does it mean by rationalizing? I think what he means is to define the rules. Okay, for example, like the one with this 辐射状, these are rules. Okay, radiosity, can I call it radiosity? Huh? Am I? Okay. Okay. Because I have highlighted some part. Maybe we should go slower. Okay. Okay. In the abstract, they propose a modeling method based on rationalizing curve folding in order to find the form variations of 1 degree of freedom origami mechanism. Okay, so we interact with a physical paper model of curve folding, and then discretize the curve folding by identifying and fixing the rulings. Okay, because curve folding actually is kind of continuously smooth surface. But in order to do the simulation, we have to discretize. Of course, I think maybe in some other research group, they are able to do continuously smooth surface simulation. Okay, but using this discretize, which means if you have a curve, then you convert it into a polyline. Okay, and technically, it is possible to use a polyline to approximate the curve as good as possible. Okay, if you need, then you just divide it into many very small line segments, then it is very close to the curve. Okay, so it's a matter of how much segment you want to define. The discretized form is a rigid origami structure. Professor Tachi has implemented a software for doing origami, rigid origami. Okay, you can download it from your website. So you just need to input your crease pattern, and then the program can simulate that for you. But we can also do that in Grasshopper using Kangaroo or some other plugin. And today I'm going to show you. I think I have shown you before. Okay, we have been using Crane before, very briefly, but I have let you know it, and there are examples. I'm not sure if you have tried that or not. Okay, and then another important thing is at most 1 degree of freedom. The form adjustment follows the discretization so that it is sure to realize a mechanism. Okay, Okay, and Tachi had a workshop teaching students to design forms based on curve folding. And I think his experience shows that the good way to carry out this workshop is through both physical modeling and also the computer simulation. Okay, the object of the workshop was to utilize the 1 degree of freedom characteristics of discretized curve folds as a constraint in the design of dynamic architecture component. So the purpose is also for designing architecture component, but also he also mentioned about dynamic, so maybe he's thinking about kinetic structure. The results showed the feasibility of the method and suggested a normal methodology for design. Okay, I think here he discussed the kinetic surface using rigid origami. Okay. This part has less to do with curve folding. Okay, here 3 important things. Okay, very brief review. Rigid origami for foam kinetic surface, and I think most common or popular is this Miura-Ori pattern and Rom-Resch pattern. Okay, Chuck Hoberman's design is not origami, but it's a kind of kinetic structure enabled by using linkages, mechanical linkages. We can also use computer program to simulate that. Okay, and especially mechanism based on quadrilateral mesh. Okay, for example, this Miura-Ori is consists of quadrilateral shapes for the mesh. Okay, and this 1 degree of freedom is very useful for designing kinetic architecture component. Okay, because of the following reason. First, the structure can be formed by thick panels and hinge. Okay, I think last time when I introduced crane, do you remember that? No? Yes? There are 3 folders of examples. The third folders of the example scripts are for creating this kind of folding structure using thick panels. So in crane, they provide component for creating actually if you use some planar material and you need a laser cut to make the folding structure, then you can use crane to make sharp drawings. Okay? Because the result it generates, you can simply use that as a configuration drawing for laser cutting machines. Second, the overall structure is controlled by one manipulator or a human user, or you can call it an actuator, okay, like a motor driving the string. Okay, because it's 1 degree of freedom, so it is very easy to control. It is possible to design a structure that counterbalance itself in the transformation. So in the process of the transformation, the structure somehow always is kind of balanced. I mean, the structure will find the equilibrium state for itself. The structure mechanism is redundant, and we can cut out holes to surface while preserving the mechanism. Okay, especially if you are able to do some structure analysis, then you will be able to find out which part you can cut out. Okay, and by doing so, you can decrease the weight, but without weakening the whole structure. Okay, how can we use origami, rigid origami, to simulate curve folding? I think this paper, he explained very briefly, but very kind of inspiring. Okay, so, first, curve folding is a piece of paper folded along curved creases. It is formed by combining folding and bending of the paper. Okay, we have a crease and then we fold, right? And then we also bend. Actually, I should use a curve folding. I mean, this is bending, okay, without creating a crease. Okay. Okay, in a geometric sense, a curved folded shape is a developable surface comprising the patches of smooth developable surface. Okay, no matter what you do, any part of the panel material, all parts are developable. Okay, even if you cut a small portion of it, the part is still developable. Even though each of these smooth patches only make relatively simple form, the existence of creases make the surface freely configurable. Okay? The next sentence is very important. Enabling globally non-developable complex surface. What does it mean? We start from a planar sheet of material. So no matter what you do, without extending it, no matter what you do, every part, it is developable anyway, right? But somehow, after you do some manipulation, it is possible to create non-developable overall shapes. Okay? I think we did it once. We used this kind of folding to create hyperbolic panel. Remember? Okay, with square, mountain, valley, and finally we get hyperbolic panel. Hyperbolic surface is not developable. Okay, so this is what it means. How can it do that? By folding, I want you to recollect that experience. By folding these squares, okay, every part of it is kind of twisted, but not really twisted. I mean, we cannot actually twist the paper without tearing it. But if we fold it along the diagonal, then it's kind of pseudo twisting. I mean, this is not real twisting, but after you have this folded diagonal, then the right to you is the left edge, and the right edge, they are not parallel anymore. So this is twisted, okay? And in this case, it is still developable because actually you have both. Okay, but then you have a lot of this kind of pseudo twisting surface put together in some specific way. Then you get the overall form become non-developable. Okay, and perhaps this is very important for architecture design because architecture is a very large scale. So if we are able to produce components which are developable, but then we arrange in a proper way, then the overall shape becomes non-developable. So actually we can use developable component, small component, and then we assemble them to become non-developable, okay, in large scale. Okay, so this is very important observation. Okay, I think a round wedge pattern is a very good kind of example. Okay, and this figure shows a planar sheet of material with curved creases and with these rulers. Okay, this parallel line, not necessarily parallel, but these lines are rulers for this curved folding. Together, they can design the shape like a car. Each smooth developable surface patch is a ruler surface, but the opposite is not necessarily true. Okay, every developable surface is a ruler surface. I think you know what is ruler surface, right? No? Okay, ruler means straight segment. We use ruler, right, to make drawing. Okay, ruler, straight. Okay, and ruler surface means if you sweep a ruler across a space smoothly, and the surface that you create by this sweeping motion, then it is a ruler surface. Okay? Or you can understand it another way. If you draw two curves in space, and then you connect these two curves with straight lines, like you divide this curve into many points and divide this curve into many points, and then you connect these two curves with straight line segment. Then the surface is ruler surface. Okay, and this sentence says all developable surface is ruler surface. Okay, but I want you to understand it is not right if you put it the opposite way, which means ruler surface is not necessarily developable. For example, hyperbolic surface is ruler surface, but hyperbolic surface is not developable. Okay? Once I've read a paper, the paper claimed, the research group claimed that they create a system that can automatically create sharp drawing for building envelope system, such as what Boris has been doing for Gomo. Okay, so they say that they have a project having a curved surface as the building scheme, and they program dissect the curved building scheme into panels, and then they flatten the panel, okay, and create sharp drawing. Okay, and they also mentioned that there are some surfaces are twisted, okay, and then they create flattened drawing for this twisted panel. Is it possible? You see, a twisted panel, actually hyperbolic surface is a twisted panel. it is not developable. So it is impossible to make sharp drawing as a planar surface, right? Okay? So it totally doesn't make sense to claim that they can do that. Okay, and then the second clause is very important. So every developable surface is a rule surface, and the ruling have non-twisting relationship with neighborhood. Okay, which means the rulings, they cannot be twisted. Okay, so they have to be not necessarily parallel. They can have different angle, but then the four endpoints of these two rulings have to be planar. If you twist, then the four endpoints are no longer planar. Okay? So if this is to be a developable surface, then you take any of the two rules, any of the two rulings. The shape, this quadrangle, has to be planar. Okay? If it is twisted, for example, then you need a diagonal to somehow fold it, then this surface is rule surface, but it is not developable. So this is important key. If you want to use folding, rigid folding to simulate curve folding, then this is a constraint which is very important if you actually write a program to simulate it. So all rules have to be non-twisting. Okay, the differential geometry analysis of curve folding by Hoffman and by Fujis and Tabachinkov give a basic understanding of how a deformation of curve fold, such as folding, twisting, effect change. Okay, the following results are useful to understand the relationship between the three-dimensional configuration and the crease pattern of a curve fold. Okay, first, the curvature of a fold line in space increases as it folds. Okay, maybe we use a paper and somehow you use something, I don't know, maybe like a key to make a curve fold. Okay, start by simple one. Don't make it too complicated. And then we try to curve fold it. Mr. Hong is the master of this paper for origami. Once he told me that when you do this curve folding, you don't do it this way. You have to use your nail and then try to make the fold. Oh, the paper is, when the paper is large, then it is more difficult to do so. Okay, anyway, what does it mean? When the folding angle is small, then the paper becomes flat, right? And when the folding angle is large, then also the curvature becomes large, right? This curve folding, when you fold more, then the curvature becomes larger. Okay, so this is the first relationship between the fault line. Okay. Second, the curved fault does not twist when the left and right ruling have the same orientation in the crease pattern. Okay? One very important thing. When we define this curve folding, actually there are many degrees of freedom, which means that the shape is not only decided by the fold angle, I mean how much you fold it in. There are some other things. Okay? And if we want to describe it mathematically, then the other thing that you are able to modify is the rulings. You can have different ruling directions. Okay? And here, I think they have a figure. He has a figure showing this. This is one example. This is all the rulings. This is the folding crease. Okay? And on the left-hand side of the crease, there is a ruling. Right-hand side, there is also a set of ruling. But he said, if the ruling has no kinks, which means it is one straight line from left to right. Okay? If this is the case, then there will be no twisting. Okay, the curved fold does not twist. What does this mean? This curve does not twist. Okay? This curve is planar, right? We can put it on the table. Okay? And when the rulers has no kink, which means when you unfold it, these rulers going straight from top to down or from left to right. Then if you follow this ruling, then when you fold, this curve will not be twisted. How can I twist it? Can I go this way? When I fold it, I move my right hand up and left hand down. Then the curve will be twisted. So it will become no longer planar. Okay? So when I fold it, I can change the motion of my both hands so to control the direction of these rulings. Okay? But somehow if I do it the way as Professor Tachi described, you keep the rulings straight lines, then the curve will not be twisted. So for example, if we have this sheet of paper, okay, and then we have a curved fold parallel to the inner and the outer arc, then when we twist it following these rulings, then you will not twist the fold line. So I think in this case it will be always an arc and a planar arc. Okay? And then the curvature will increase when you increase the fold angle. Okay. So this is the second observation. And the third observation, the folding angle, actually I don't understand what this is. Complementary angle of the dihedral angle. A lower curved fold is constant when the ruling reflects the curved fold in the crease pattern, producing uniform curve folding. Figure 4. Okay. what does this mean? We have ruling on the left-hand side of the crease, okay? And we have ruling on the right-hand side of the crease. Here in this figure, he shows it in blue and red. Okay, in this case, you consider this curved crease as the line for reflection. And then you follow the tangent direction of this curve, and then you mirror the creases, the rulers on the left-hand side to the right-hand side. Okay, this is trivial, but this one, you see, every blue ruler, if you reflect this blue ruler based on the tangent of this curve, then you get the red ruling on the right-hand side, right? They are reflectional, symmetrical. Get it? Following this crease, this curved crease. You understand what I say? You get it? We have a curve, and then we have ruling. How can I get a reflection of this ruling to the other side of the curve based on the tangent of this curve? So we find the tangent of it, right? At this point, we have the tangent, right? And then we draw another line. Having the same angle. This angle is equal to this angle. Then we get the reflection. So using Grasshopper, we have this mirror component. So we mirror this curve based on a plane. Okay? If you add one vertical vector, then you make this tangent line become a plane, and then you mirror this ruling against this plane, then you get this one. Okay? So if all rulings comply with this rule, then when you fold it, the angles of these rules are maintained constant. Okay? This is the rule on the right hand side, this is the ruling on the left hand side. And then when you fold it, they can become sharper and sharper. Okay, but throughout all the surface, all the ruling on the left hand side and the right hand side, they maintain the same angle. Okay, and sometimes when you, as an architecture designer, sometimes this is very important to you. Okay, for example, if you have a pitched roof, then you know that the angle anywhere inside this pitched roof are the same. Okay, this is the simple case. But when you have a twisted ridge, but then you still have the same angle for this pitch all the way along the roof. Okay, and like even if you have smaller fold angle or larger fold angle, okay, they will maintain the same. So this is the third observation. And then 3D relation, uniform and non-uniform folding. Left, uniform angle folding using mirror reflection. This is Okay, you see. This one follow this reflection, right? Rulings on the left hand side, and then we take a look at this crease, curved crease. Then you reflect again it, then you get the right hand side, right? So when you fold it, it is 100. If one position, the folding angle is 135 degree, then it is 135 anywhere. Okay. But if your ruling does not comply with this refractional law, then when you fold it, the folding angle can be different anywhere. Okay, such as this. So this is non-uniform folding. Okay, I think you should read it more carefully. Okay. I think all this part is very important. Okay. Using the difference in the behavior, we can design patterns in the following two steps. First, we fold the paper to set a crease shape to design overall approximate form. Then, by reversibly and continuously bending the folded shape, we can find twisted or non-uniformly transforming variations. Okay, what does it mean? First, you fold it, you get the overall shape, but then you know that you can twist it. Okay, so that to find out what is the shape that you need. So I think this is also what he means. The workshop, we need to work on both the physical model and the computer model. Okay. Later we are going to do some simulation on crane. Then you will know it takes a lot of work to define the rules. Okay, but when you do the physical model, it's very easy for you to change the rules. It depends on how you twist the whole shape. Okay, and there are some other examples. In this case, this cone actually is kind of bistable configuration. What does it mean by bistable? When you intersect this cone with a plane surface, then you get this ellipse, right? And then if you use this ellipse as the curved crease, folding crease, and then these rulings as the ruling, then you can create this kind of indented cone. And this is also stable, and it is also from a planar sheet of paper. But it is impossible to have a continuous transformation from this cone to this truncated cone, right? Because you have no way to transform this cone to this one without tilling the paper, or somehow make it very ugly. Okay, but mathematically, the two shapes are all kind of balanced. Okay, so this kind of shape is kind of called I don't quite remember the form, the term. Bi means two, right? Bistable. Okay, so which means this kind of creasing configuration. Okay, when we unfold this cone, then we get this one. This is the curved fold. Okay. Somehow, if you have this, then by folding it, you can get two stable shapes out of this crease pattern. Okay, and here elastic transformation with the change in the ruling position, which means if you want to transform from this shape to this shape, they have the same crease, but they have different ruling. Okay, somehow it is possible to have continuous transformation between these two. Okay. Rigid curve folding, the non-twisting property of developable surface forces the adjacent rulings to form a planar quadrangle. Okay, I just say that, right? If you take adjacent rulings, then the two adjacent rulings will make a planar quadrangle. Okay, and this is a very important thing for them to try to simulate, to have computer simulation of this crease, curve crease folding. Interpreting the 2D and 3D or 4D is a simple method of defining an angle constraint between any two faces. Okay, 2D, we draw it on a planar sheet of paper. 3D, when we fold it, it becomes a 3D shape. When we have a continuous transformation between one 3D shape to another 3D shape, then we have 4D. When we design kinetic structure, actually we need to model the structure in 4D, right? Okay, PQ. PQ means planar quadrilateral mesh. Okay, this is also very important. Planar quadrilateral mesh is very important for architecture construction because all the quadrangle surfaces are planar. Then it is easier to design and fabricate. Okay, here, see, bistable structure. This is what I just mentioned. Most patterns that represent curve folding in 3D are continuously rigid foldable. If we add a triangulation crease to emulate a small amount of bending of the panel. Okay? Okay, I think I've explained this. Since there is an original physical model, we can expect that there is at least one 3D configuration that is valid even without triangulation. I mean, when it is formed by this kind of PQ mesh, planar quadrilateral mesh, then you don't need triangulation. Okay. And here talk about how to build a thick model of folding structure. You can find that in Crane. So you can make sharp drawings for the top layer and also the bottom layer. And then you attach and glue them together, then you can, and also make the hinge, and you can make the folding structure. Okay, and then this part, I think he talked about his workshop. His workshop, I think it's in Japan. Okay, the student working on this workshop. And their design, and they use thickened panel to make the structure. But the design is from curve folding. The result is not curve folding. The result, they are all planar material. Okay, that's it. So please download Crane, install it. Okay, curve folding. This is another paper. Okay, this is by this very famous person. Again, Helmut pattern. Okay, if you want to find something interesting for architecture geometry, you will always get it if you use this professor's name as your keyword for search. Okay. Okay, I'm not going to go through this. He talked about algorithms, how you can simulate it. Okay. These are PQ mesh, planar quadrilateral mesh. If you want to do research on this, then you have to read paper. Yeah. Okay, so let's go to Grasshopper. There's a file I uploaded. I call it, oh yeah, curved folding with crane. Okay, and I use crane, which is a plugin for Grasshopper. I think maybe 2 months ago or 1 month ago, I've been showing you some examples. Okay, okay, let me show the first example. I have to turn off this part. Okay. How come it becomes so complicated? I should hide this curve. There's only one there. Why I cannot hide? This one is layer 2. How come? It is layer 2. Okay, anyway. Okay, this is the solver, crane solver, and I turn it on. The blue and the red, I don't quite remember. Maybe the blue is the valley fold and the red is mountain fold. Okay. Rigid mode, I turn it on. For all quadrangles, I want to make it flat, and I want to prevent from 180-degree folding. Set everything, and then I can start to fold. Okay, so the blue one are mountain fold, and the red one are valley fold. Okay, so you see, there is no curve, but we can discretize the curve into segment, line segments. And somehow it still look like a curve folding. Can fold more until the fold is reaching, approaching 180 degree, and it prevents from conflicting itself. Okay, how can we do that? Then we can reset it. First, we need to draw the crease pattern. Okay, and of course there are many ways to do it. Okay. I think here I use one curve, draw one curve, and then the sheet of paper is like this square. Okay. First divide it, okay, because I want to get the point and then to create the rulers. And find the range. Sorry, no. Find the coordinates, x, y, and z. Okay, and then use this x and y coordinate to create two set of points on the top and the bottom. Okay, and the top y coordinate is 10, the bottom y coordinate is 0. And then remove the first one and the last one. Okay. For this, you see, before it consists of 11 points, but here I remove the last one, so this point will be gone. Okay, cool, -1. And this one, remove the first one. So I can use these two lists to create many different things. Okay, these two lists together with these two lists, then we make surfaces because I want to create a mesh. So this is one set of quadrangles on the right hand side of the curve fold, and these are quadrangles on the left side. And then I convert this, they are rects, they are surfaces, convert them into simple mesh. Okay, merge them and then join all the mesh. I need to do one more thing because the vertices are duplicated. So right now, if you look at it, it has 80 vertices with 20 faces, which means many vertices are overlapping each other. So I need to weld vertices. So after I weld it, before it has 80 vertices, after I weld it, now it has only 33 vertices. So now this is the mesh that we can use for this folding simulation. And this component is from Crane. So have you already installed it, Crane? Okay. So Crane. Then we have this solver. Okay. How come I cannot track it? Sorry, this is not a solver. We have to create a C mesh. I think it means Crane mesh. It's different from grasshopper mesh, but we need to provide a grasshopper mesh for it. This one. C. Okay. There are 3 different ways, actually 4 different ways to create C mesh. Okay, I think we want to specify mesh and the MV lines. You see this one? How about the other one? triangulated, if you also want to specify triangulated creases, with this one you cannot specify triangulated creases, which means if you have quadrangles in the mesh, then the component will simply choose one diagonal for you. Okay? But if you want to have control on the triangulated crease, then you have to use this component, because then you can specify what is the triangulated crease you want for each of the quadrangles. Okay, so we use this one. This is a mesh, and we have to find out all the mountain fold and all the valley fold. And in this case, it is straightforward. Take a look at this curve. Okay, if you look at from this side, then it's kind of concave, right? So on the concave side, there are valley fold. Okay. On the convex side, it is mountain fold. And also, the fold itself is mountain fold. Okay? So, when we create the mesh, we also find all the curves. Okay, of course, there are some details, but anyway, somehow we find it. So, we create a C mesh, crane mesh, and then you give it to this solver. Okay, and C means you can have a set of constraints similar to kangaroo, like you can have anchor, or you want to pull two vertices together, okay, or you want to define some crease line and then set up, angle it. But so far, I'm not quite successful in this. And this parameter set the folding speed. Okay, and again, this is a numerical analysis process. So by numerical analysis, actually, it doesn't guarantee to have precise solution. Okay, somehow, I mean, this is involved in resolving a large set of mathematical equations, and somehow it uses like a numerical approach for it. So it doesn't solve 100% correctly on all the constraints. Okay, so you set the rigidity. Okay, if you set it larger, then it will try harder to keep it all the shape very precise, exactly like what you have designed. Okay, but then the computation becomes more and more difficult. Okay, so it is a price that you have to pay. Okay, so if you, okay, and then this is the viewer. Okay, and turn it off and on, reset to its initial, and then you click it to fold it. Okay. And then how do you get the result? You get the result from this C mesh. Okay, because then you have to create the 3D model, you have to maybe go on to do your architectural design. So you can crane and then deconstruct C mesh. So after it is folded, you get this C mesh again, and then from this C mesh, you get a grasshopper mesh. Grasshopper mesh from here. So this is a grasshopper mesh. Then you can bake it, you can do whatever you want on it. Okay, and you get a mountain fold, valley fold, boundary, unassigned. There might be some edges, and you haven't assigned it as a mountain or valley fold. Triangulated, and all the edges. Okay, so this is how you can get the result. Okay, here, if you make it true, then it shows all this triangulated edge. If you make it false, how come it still shows it? Here? Okay, yeah, that's right. So if you this one is false, then it doesn't show the triangulation, but if you make it true, then it shows. Okay. Any questions? This is the first example. And then the second example. Oh yeah, here. But how come the other one is still there? Okay, 40. Oh, quadrangle spread on, rigid mode on. Okay, this is important. You have to set these three on. Then you can follow it. This curved line, I want to put it that way. It doesn't want to go. Okay, so you see this time the curve is kind of edge-shaped, and you can see. Let me reset it. You can see that the mountain and valley fold depends on the curvature, right? This is the S shape. So here, if you look from this side, this is kind of concave, okay? And this part is kind of convex. So they change. This is mountain view, this is valley view, valley fold, and here become mountain fold and valley fold, depending on the curvature. When we draw a circle that tangent the curve, then the center of the circle can be either on the left-hand side or on the right-hand side of the curve. Okay. So when the creases, the rulings are of the same side with the tangent circle, then it is like mountain fold. Of course, I mean, depending on how you look at it. I mean, if you look at this way, then it's mountain fold. If you look at it from the other side, then it's valley fold. But somehow I just want to say that you have to be careful whether the tangent circle is the same side of this ruling or the other side. Anyway, on one side, if this is mountain fold, then the other side should be valley fold. Okay? And here, there's a point. So it will show you the center, the middle point of all the edges. Okay? And of course, if you want to do it manually, then you can always display a number. For example, like this one. Okay, you can display, I cannot enlarge it, okay, but I think you have all very good eyes, so you can see it. So you can check which edge is the one that you want to set constraints on, then you simply type in the number. But I think this is not very smart. So a better way is that we know which are the lines, and we need to have a process to find out what is. Oh, I forget to record it. So we have two students from China. They cannot see much. Oh, Boris, are you doing the video? Oh, okay, good. Okay, so no problem. Okay, but if we want to find out the index of these edges, I've tried a number of different ways, but I think this is the best way. You see, these are the center of all edges. So now these are the two set of creases that we want to set constraints on. Okay, so how can you find out the index of them inside this C mesh? Okay, first we also find the center or the midpoint of these creases. So which is to get the starting and end point and then divide it by 2. Okay, I've been trying to use this one, this point on curve, but somehow it is dangerous. Why? It shows you only the first digit, right? It doesn't show you the second, the third, and so on. And somehow, I mean, when you are working, maybe somehow sometimes you will try to drag this one, and you may have changed it without knowing that you have done it. Okay? So in this case, it is no longer 0.5. Check it. No data. Oh, because I have no curve. Okay, you think these are the middle point, but in fact it is not, because you have accidentally changed the value of it. So this is dangerous when you want to do something like that. So I decided to use this average thing. So to find out the center location, and then you have to find out these points and this set of points. Some of them they are duplicated, and you have to figure out what are them and what are the indices of them. So I merge the list of points together, so they become one list. Okay, these are the points that I want to find out their indices in this set of points. Okay, so I merge the two lists together. This set of points first, and the point that I want to find out follows. Okay, and then core points, which means a core duplicate point, which is in vector point here, core duplicate. Because one very good thing is that it finds out, okay, it will remove the duplicated point, but this is not what we want. And this is the indices. Okay, I think all the -1, when you look at this text panel, the -1, which means the places where it finds duplications. Okay, but this one is more useful. This is called the balance, which means the number of occurrences or the number of duplicated points. Okay, for the list, the first one has got 2 points on one location, right? So we know this is the index that we would like to know. Okay. Aha, I think maybe I know what's wrong with it. 145. Yeah. I know what's wrong. 145. No, not necessary. Okay, so after this, I just need to compare this list and to see which number of this list is equal to 2. Okay, then I get a pattern of true and false, and I use this true and false to cool the pattern of the whole list. But because I just want to get the indices, so I check the length of the list and then create a series of numbers from 0 to 144, and then cool all the things that out. Okay, and in order to check the correctness, okay, you see, they are correct. So I have select all the correct indices for this point. Okay, so I know that this is the set. Actually, I should connect here. Okay, and this is the component to set a constraint on the fold angle. So use this set of HID to identify all the folds, and then use this number to set the angle. Somehow it wasn't successful, so I disable it. Okay. I hope that eventually we can control the angle of the fold. Okay, maybe we can take a break for 5 minutes. And Victor, after the break, maybe you can introduce how you did it. Okay?你就直接当了我的程式，就在你那边的操作过去。Parameter variable x has an invalid name. 哎，怎么会这里怎么会变成这样？
我也不知道哎。
你有改过吗？
没有哎，还是我们直接改成 x，还是就好了。
应该是 x 就好。我不知道。
那我们直接打这个。好。嗯？
还是一样的。
哎，好了。
哎，可是你的为什么会变成这样？
我也不知道哎。
那我的嘞？
所以老师的看起来是好的。老师的看起来是好的。
哎，奇怪。那我应该是不会去把它改成 variable x。
还是要打开的时候他自己跳。
应该不会。
好不？
他会这样就很凶。那个 Victor， 你会用你自己的那个 laptop？ 那个你是自己写的，还是你用了什么？
都用 Kangaroo 啊。
哦，用 Kangaroo 做。
对吧？ 不对？
它的软体上面显示的，而且我还把它调到4超快，才有把它正常开出来。
是绿色的那个，
我上次拿的。
就是刚刚说的结果，是我一次可以选到这个人的那一个点，其中一片的那一个小圆圈。然后它现在
你这样是有这个，你要把它分成。
对，我现在有这个，就像我原本的这个状况。
然后你永远都是确定是4个一间，你永远不会变。
对，我确定的。继续分吗？
好，结束了。
分完了吗
00、01、02、03、10嘛，然后你有每个4个，就是说你要去选其中一个，你是去选。然后都会选到这个。好，结束
所以如果我这边打，如果我这边只打1的话，它会选到什么？
你没有1这东西，它不会选到哪里。
所以我要看这个，对不对？
如果说你想，例如说这4层，
对的
你
话，
要打0，然后后面是星号跟随便，再跟随便。
它申请。
text class。
Maybe just just
会不会是它同名是一样的吗？
有时候这样子。
哦，好。
就是 tree branch 的话，你一定要给它完整数字。如果你要有变数的话，你用 split tree。split tree 它都会跟你说，你选到你是 P，然后你没选到是 P，你选到 P 这边往这个 curve， 你选到这个是，应该会选到这个，有16条。
我照理来说会选，但我想错了。好，我又遇到问题了。我要的并不是这4个，我要的是跨了240个之后的241个。就是它并不是个4，它是0跟。
你要选这4个的那个，
就是它会跨着，对，它会跨着。
你现在都是要选这4片的，对不对？然后你总共有几组？2、4、6、20、60、80、60。
对，现在的0跟现在的60跟现在的。
所以它的顺序是什么？它顺序会是这样一条一条下去，然后再回来，然后再一条一条下去又回来。
对，它现在是这样。它现在是第一片。
那真的怎么哦？
什么意思？
所以你有60片。16层那个点。哦，这样就结束了。
你说了吗？
然后你说你每4个要1层。
对。所以 partition 是把它分成一个分出一个，上分一层。
4层，就是原本有这些，跟你们讲这样，它就是1层进来一个。然后 partition 之后，我们都跟他说，我希望再多1层，然后每1层里面有4个东西，然后他都会拿你这边的4个放在一起多1层，然后下4个再放在一起多1层这样。
它的宽度不一样，跟深度比较。
所以你现在这边00啊、01啊，然后每个都有4个。然后如果你要其中一个4个除以。
为什么？等一下，我又想错了吗？跨。
那16个手机有什么事的？
你把圆放大一点。哦。对吧？看不到吧？
这哦。
很遥远，为什么？
你确定有60个？
还没排4个。这样子，为什么它现在到底是长什么样子？16个，所以你这是要先分60，我们是要先分60个。
你这顺序到底是怎么？
下面的。
先分4个。这边4个乘以60，所以我先分240个。所以就会有4个。
可是它原本就是4个4个。
如果这边给它，我选第一层的话，会所有的左上角，第二层所有的左下角、右上角、右下角。
好了。
你会在乎这4个顺序是什么东西吗？还是怎么算？
没关系啊，他现在不就哦？你说如果我打掉它之后，他就会这样直接。
那现在你得到的4个是
1、2、3、4。
对啊。
大家就这样。我想一下，这件自己中断吗？主要。
那你以前看到形式吗？没有，都没有。这个是测法师。
我们组的哪一片？
就在做那个模拟的。我刚刚有试了一下，果然像你讲的那样不行，它怎么样拉起来？
坏掉。
不是坏掉，就是我刚试着用 crane 去做你们要做的这个东西。
我觉得比较像老师
啊
说的这个。
没有，我刚刚试了，不行啊。我刚刚讲那个方法是不行的。
但是老师是把它集中在那个点，我们的还有这个。
哦，你说再加上这个
对
就可以了。
我觉得应该可以。
有可能。对，有可能。但是这个可以做的很小。
对，如果很小的话，其实也接近。
还是做一个圆。
这个圆啊。
对。
这个圆是像老师的那个刚那个三角那个圆锥。
一条线过来，然后这边是一个
直接把它切掉，变成空心的，它这样子再做放射状。
我回去给试试看。要先上课吗？要先上课吗？
啊，已经在量产。礼拜三有去跟那个工厂那边讨论然后他们最近要，这样吧，可能会没有那么快。你有那个线条？所以我要期末回正的事情，还没跟帮我跟他说一下。那你量产有确定一定可以装得上去，不要这样在量产或者装不上。没有，他现在也是要测试的开一个7%，啊，然后你们的那个销售量多少？有没有上资料？好了，那就没有问题了，没有问题了。主要是我们那个我会给他们报价，然后Victor那边他是用那个 Can you tell me for instance, how we did it with subtronic?
Of course, I have to tell him. But I can remake it now.
你可以切，他会切一点最大，那个很小的一点，他们要切一个，哦，然后中间那个很顺拍的，然后用，我想办法用那个，曲线。我看到这个机器，如果用不同的机器。他们都要维持这个，还有场内，还有一个是场内，因为谁的点法，有外面还有还有谁。
Is the romish? This is the water.
Yeah, that's the one.
他们先应该看。我真的教这个可以是，所以你们好几个别的，风景线，说明那个。
You know, the first time I tried,
你要切多少位置？
I almost think that that you receive also. Like 20 hours.
I use it for my undergraduate project.
Undergraduate project, you use Visual.
Yeah. For basic, for the first or second semester, we do
You use thick material.
like 400 grams.
不知道这个传给我，我在想一下。Because Kangaroo doesn't read curves, so I have to change these curves, which is a nerve curve or a planar curve, into polylines. So I have to divide this curve into points, and then shatter this curve at those points, and then recreate it with a polyline. So it goes from a smooth curve into segments of straight lines. And using these segments of straight lines on both sides, I can draw a zigzag between the endpoints, which would generate this. So that becomes, I guess, the center. And so I have one side, which is, so the reason I'm drawing this zigzag is because I'm trying to control my mesh. So if you normally, if you take, let's say, when your surface, oops, what happened there? So normally if you turn like a surface into a mesh, it will have these divisions of triangles, and these divisions you can't really control if you just let the program decide. It will do this really weird divisions of triangles. So what I'm trying to do is I'm trying to control the divisions of triangles. So instead of letting the program decide what the triangles are, I create the triangles myself. That's why I'm drawing the zigzags. Okay, so the zigzags combined with the polylines from the edges, basically these triangle panels become my mesh. So what I do is I change them into a surface that is a triangle on each side. And then I can put them into something called a mesh breadth. Basically it takes a breadth, it converts into a mesh, but it has an option where I can use mesh settings, and one of the settings is as simple planes. So if I put a triangle into it, instead of trying to subdivide it into more triangles, it will just take that triangle and use that as a mesh. So from here, this mesh, if I take it out, you will see that it's exactly the same as my zigzag, because I've already simplified my surfaces into triangles. So from here, it's basically the same thing for the flaps. The flaps is just, what did I do for the flaps? The flaps is just starting from these curves, you have the two sides, and then you can look for the discontinuity of the line. So basically a discontinuity is, a discontinuity is when a line changes direction. So because this is basically just two straight lines, so if I put this in a curve, you'll see that I is just two straight lines. So the discontinuity would be where it starts, where it changes, and where it ends. That's why I have 3 points for discontinuity. And because it's just two lines, I know there's always going to be 3 points, where my second point, which is 1, would be the one that I want, the midpoint, or the very far edge of the flap. So I can take the 3 points, select the one that is the furthest one from the flap, and then just draw a bunch of lines between this point and all of these midpoints. So it's just a straight line from this to this, which is here, I believe. No, not here, somewhere here. Okay, so yeah, it's just basically a straight line between the 2 points. And then those points combine, so these lines combined with, no, not this one, with that edge polyline, I can again create triangles that would become meshes. So at this stage, I would have basically what looks like the same panel that I input into Grasshopper, but converted into a mesh with the division of the curve that I want, and all of these are simple, very simple triangle meshes. So from here, you basically start saying, okay, all of these points, I want to put a load on them because the material itself and gravity stuff. So all of these points, so you have load. And in order to not have this, because of how the mesh is drawn, there will be duplicate points. For example, this point here, there would be one from this mesh. There would be like, this point would be duplicated 5 times because it's a shared point between this mesh, this mesh, this mesh, this mesh, and this mesh. So at this point, there will be 5 points. And if I just input all these 5 points, this location would experience 5 times more forces than other points. So I would have to use a remove duplicate points to remove all of that duplicate ones, and so there would only be 1 point at where meshes share a point. And once all these duplicates are removed, I can take all these points, put a load on them, and this load would be just like gravity, so it's z negative downwards. And the weight is something that you can't tinker with once you have all the settings, because it's not an absolute value, it's relative to everything else. So there's no correct answer. And then you can take all the lines, all the edges of this mesh, and tell Kangaroo that you want to treat it as a line that doesn't change distance. So you just put it into a length component and it will try to maintain its own length. Then here you would have your anchor points. So you would also have your anchor point. The idea when you're folding this is that you push in from the 2 sides, and once you push in from the 2 sides, the flap itself will move up. But if you try to simulate this, it's always going to fail because of how the simulation works. So instead, the correct way of doing it would be you give it 2 force, you push 2 force up, and then you tell Kangaroo that these 2 points cannot move away from your XY plane. But then if these 2 points cannot move at all, this whole panel would not move because all the lengths would have to stay the same. So these anchors, these 2 anchors, which is one here, one anchor here, and then the other anchor is just the other point. So the other anchor is here. And what the anchor has is a setting for target. So you can say, I want this anchor that is right here to move to a certain position during simulation. So what I've done is I told it to move in. So it moves in slightly, and then on the other side is the same thing. This anchor point moves in slightly. So once these 2 points, these 2 anchor points move in very slightly and becomes an anchor at a new point, there will be slack on the material. So once you apply upward force on the 2 sides, there will be slack on the material, which allows for the deformation of the material. So that's basically everything, I think. What's this? Yeah, that's basically everything. So here is the 2 points, 1 point on this flap, 1 point on this flap, and the force is just going up. It's not, okay, the force is not perfectly up because it depends on what angle you want. So for example, here I've said that I want 45 degrees on the flaps. So I have to do like a trigonometry calculation. So I find out that it's tangent, so you just use the tangent, and then you can figure out the value between, if you want a 45-degree flap here, you have to figure out how much force you want upwards and how much force you want on the planar, so that when these two forces adds up, it becomes a 45-degree force that is pulling the flap up and out so that it maintains that angle instead of becoming a flap that looks straight up like that, right? So that's a calculation where you have to figure out how much upward force you have to apply according to your trigonometry. And then all of these values will be put into a Kangaroo solver, and you just simply ask Kangaroo to solve for it. So that's the basic law of it.
Very nice way.
Yeah,
And I think it is also very efficient. Right?
Yes, but it creates problems.
Right.
So for example, here you see that this line is connected on the flap to the other side. So the force that is pulling up here gets transfers down this line to this edge, which pulls this point upwards. So that's why on this side here, I created a force that is solely on these points pushing it down, so that this point doesn't get pulled up by this force. There's slight problems. It's not perfect, but it's indicative.
Have you checked the distance or the length of all these lines? Somehow in the simulation,
It gets changed, but not.
crane is kind of, I would say it's kind of a part of it. Okay, in rigid origami is a standalone program, so that you can download from Touchit's website and then run it, and then you can export the result back to Rhino. Okay. And he has kind of design mode and the simulation mode. A design mode, he means that you can drag or you can manipulate somehow the folded structure. Okay, but then, okay, in crane actually you can set the rigid mode off. When you set the rigid mode off, it means that the simulation will try to change your crease. So if you set your rigid mode off, you can use your mouse button and then you press the Alt key and you can drag the 3D form. Okay. And then when you drag it, it modifies the crease pattern. Okay. And then after you have done that and then you think the shape, overall shape is what you want, then you unfold it. Then you get the new crease pattern and also the overall shape. And then that can be used for shop drawing. I think I have shown you using crane to design a chair, remember? Remember? I haven't done it? No? Okay. It's kind of a curved folding, and you can, oh no, not curved, but it's only with straight creases. So you can fold it, and then the planar sheet becomes like a chair, and then you can set a set of constraints. For example, like the chair, the place where you sit on has to be horizontal, right? So you can set a constraint on that, and the supporting of the chair has to have equal elevation, so you can set constraint on that. But in addition to this, you can pull the chair so you can change the overall shape of it. Okay, and when you do that, it will start to modify the boundary of the planar sheet of material and also the crease pattern. Okay, and after you think you finish your design, you are satisfied with the final shape, then you export it and then you can unfold it, then you get your shop drawing. Okay? Yeah, so maybe next time I can show, but I didn't show that example to you. It is one of the example in crane. Okay. Okay, maybe next week. Okay. Okay, good. Thank you, Victor. And I hope all your projects going well. Okay, no problem. Okay, and have you get the receipt for the material that you have bought?
但我们没有报统编。啊，不过我们只有买少量，我们还没去买全部。
Okay. 那个 Boris, you have to let everybody knows the 统编. You have posted already. Okay. Remember when you get the receipt, the 发票, you need to put on the number. Okay. And then we have a project so that we can pay from that project. You don't have to spend. Okay. Good. So see you next week. 那个你们那个好像没那么容易，要再想一下。
真的。
看看 Victor 有没有帮你进去。他们那个造型要怎么样？
我有疑惑哦。
造型
等一下，我对你的说有疑惑。
我也有疑惑。让我跟着。你问他的，我问你。
我们想要跟你们借个1-2。
好啊，1-2条哦，因为我们都穿上去嘞，你们要怎么
所以你们没有多的。
我们没有买多的。我们可以拆下来借你们用。
我们拆旧的给他们用。
旧的很粗哎，你们要哪一种 size？ 这个是，你说片子。
这个可以吗？
这个是，
如果是可以，
这是2mm的，这是1mm的，然后这个是1.5的。超肥的。我们是用真的哦。
你们这样穿的那个，我们拿冰的给他，冰放，然后他就会。
有这边，这个是1.8。
那你们这个要裁是怎么？你们要自己裁还是要请那个？
我们把雷射切割档用好了。
OK， 所以他妹妹会帮你们裁。
对。
然后要折要自己用手折嘛。
折。
我们用那个，就是用
工具。
对。
然后用这个。
OK。
我们大概会有120左右。
OK。有没有多厚的铝本？
我们用我们现在选。
0.5。
我们现在有这2种，就是3mm，然后这个是2mm。
0.2mm。
0.2mm、0.3mm。
我们偏好这个。
OK， 比较薄。
比较厚的哎。
哦，比较薄。
是整个。
这个已经有点像纸的感觉，我们担心到时候那护柜会不会一下就变形坏掉
？OK， 没关系。好，那就0.3的了。
没有差多少钱。
没关系，没关系，这广告会出现。
谢谢广告。
谢谢广告。好喽。
他也希望你们毕业以后到他那边去工作。如果有兴趣。
好啊，要做什么？
做建筑皮层的设计啊。
真的。
真的。
那工具是什么？
工具就是电脑。不过也会需要到工厂，你们可以去问 Boris 说他都在说什么，也需要到工厂去了解你们要怎么做。就是说需要的知识很全面，就是说你们都是学建筑的吗？
我是土木背景。